Okay, so it's very nice to see old friends. And so thank you for the chance to see you and for the invitation to give this talk. So the title, you see the title. And before I start the talk kind of more formally, I wanted to give some motivation for the whole story. So, so it's kind of an outline or motivation. So I'll start from analytic motivation. If you, very elementary one. So if you consider differential equation like df over dz equals lambda divided by zf, of course you can solve it. But what you learn doing so that you can recover the exponent of 2 pi lambda topologically. So this is just a monodromy of solution. Actually, you recover this way lambda mod z, but this is what determines equivalence class of this differential equation, which we consider because we also consider allowed to do changes like that. So that's precisely recovering topological is differential equation. Then you can consider a more general equation, a more general example. The next one would be famous result of Riemann, that second order differential equation with 3 regular singularities is the same thing as its monodromy, representation of the fundamental group of CP1 minus 3 points to SL2C. And the more general effect of this type is the following. So you take differential equation like that equals sum m by m matrices AI divided by Z minus AI F. And so what happens here is that you have plane, you have finite number of points like A1, A2, and so on, AN. And then if you consider the monodromy of this differential equation, which is just given by representation of, so I assume here that there is no singularity at infinity of CP1 minus these points to group, let's say, SLN or GLN C, depends what you're doing. That you can put GL if you want. Then this set of equivalence classes of presentations, it determines the coefficients of this differential equation. It's one-to-one correspondence. But then there is an interesting new feature that these points AI, so they can vary. So these points can vary. And of course, the monodromy doesn't change, but the coefficients AI, they depend on this. And so we come to the following picture, that in general, we have sigma, a Riemann surface. And then we have a differential equation, which is a vector bundle on sigma. Sigma has punctures with meromorphic connection with now it depends. I can say so far regular singularities. In a second, it will be any singularities. Regular means poles of order 1. Yes? And punctures. And then there is a classical fact that we can consider the space of all such differential equations. So let's call it M Theorem with regular singularities on the sigma. Sigma so far is given to us. And it is the same thing as local systems of rank M on the topological surface S underlying sigma. But now I can actually write here for now the sigma. But now the point is that this is all sitting over the moduli space MGN, because the points and the surfaces get data. And so the classical Riemann-Hilbert correspondence says that we have an isomorphism here for given point sigma sitting here. But then you can vary sigma, and so what you get on the right hand side, you have a local system of moduli spaces. Let's write it stacks. And so you have now two stacks. One is Theorem and another is Betti. And so Riemann-Hilbert tells us that they're equivalent as a family of stacks over this moduli space MGN. So that's the Riemann-Hilbert correspondence. Now, the right-hand side, this local moduli space of local systems is a topological object. And the very fact that it's a local system can be expressed as follows. You have the mapping class group, which is defined as a fundamental group of this moduli space MGN. And this mapping class group acts on the Betti moduli space, on the moduli space of local systems. Okay, so that's a very well-known description of Riemann-Hilbert correspondence in the regular case. Now, I assume that we're talking about irregular case. So in the regular case, the pictures somewhat different and somewhat similar. So the first thing, of course, you notice that you can consider any function like e2 minus lambda 2 over z square minus lambda or z, it doesn't matter. Sorry. Lambda 1 over z1 minus lambda 2 over z square, and so on. And this function satisfies some differential equation, but it has no monodromy. So the first thing you can see that if the differential equation has irregular singularities, then monodromy is not enough. You might multiply it by something like z to alpha if you wanted, so it does have monodromy after this, but in general, monodromy is not enough. So what is enough? So how to deal with this? How to have analytic Riemann-Hilbert correspondence? And so the main idea is that solutions in this case look something like that. So you can have something like z2, okay, sorry. e2, let's say logarithm z, maybe raised to some power, maybe with some coefficient. And it's a kind of monodromy term. And you can have a term which is e2 some function that's called f of z. And f of z is a Poisson series. Some, I don't know, lambda I z to I divided by d, where this is Poisson series of negative exponents. So z is a given integer, and I is integer, which is bigger than 0, I integers which are bigger than 0, and this is a finite sum. So you can have such a Poisson series, and then this Poisson series produce some kind of topological invariant. Namely, what you do, you consider the following curve. You consider function, take exponent of a real part of this f function, which you restrict to some circle of small but given radius epsilon. and then also record the angle by multiplying by this exponent. So, and then if you consider what kind of curve you get a picture like this. On the W plane, you can have some, I don't know, something like that. And so this is the graph of this function. And so what you learn from here, looking at this particular picture, that actually you're talking about two-dimensional space of solutions. And whenever you consider some array, what you can do, so once again, this is a formal solution. This function is a formal solution. But then there are actual solutions, and they behave as follows. So if you take any generic array, then there will be two-dimensional space of solutions, and one of them will be growing when you go to 0 in the slowest way, so you can distinguish it from the others. And then it defines some one-dimensional subspace. And then will be everything else. So you get a filtration. You get a flag in space of solutions. So this is basically an analytic introduction. So I was very brief and fast. And all I wanted to take from all this discussion is the following conclusion, that if you want to study irregular singularities, and actually it turns out regular as well, you have to deal with collection of flags. Why flags? Because on every array you see here flag in the space of solutions, which is filtered by the order of growth from smallest to biggest when they go to 0. But when you change slightly this flag, you change slightly, I mean, it changes continuously, but then it jumps at that moment. So when you're coming through the crossing point, it jumps. So there are some jumping rays where situation is different, changes. And if there are finitely many of them, and in all other rays, you see some filtration. So this means that you have you have a collection of flags, and it turns out that your topological data is described by this collection of flags. This is basically the Stokes data. I have to be more specific how they talk to each other. There is some genericity condition. And this is local picture. And also there is a monodromy of global solutions to Riemann surface. So this kind of data, and again, I will say this in much more precisely in more detail in the second lecture, but this data is this kind of Stokes data. So it's data of topological origin. And the analog of Riemann-Hilbert correspondence in this case works as follows. So you have Moduli space of all differential equations, all of them on your sigma. And first of all, any differential equation has some discrete invariance. Like, for example, the dimension of the space of solutions, but not only. And also has continuous parameters. So when you talk about discrete parameters, the picture is the following, that you have your Riemann surface. It has some punctures, and near these punctures, you draw the curves I was talking about. So there are some kind of curves which you draw here. And the isotopy type of those curves is also a discrete parameter, and actually it keeps information about the rank of the system. But it's a little more complicated than that, because you can add also some local systems on this on this red arcs. And so, but I don't count these local systems as discrete parameters. Only the dimensions are discrete parameters. So basically, keep in mind that what all you have as discrete parameters, you have your local system L, and you have some vector of dimensions, because you might have some local systems on connected components of this red arcs. So this is discrete data. And so if you give yourself discrete data, then there are these Theorem and Betti stacks. So Theorem stacks means all differential equations with this data, which have this prescribed data. And then there is some kind of modular space of stock data, which I can denote this way. And each of them is fibered over the same space. So this is kind of wild Moduli space. And it's fibered itself, of course, over MGN, but it's much, much bigger. And then there is a analytic isomorphism between these two complex algebraic varieties of very different algebraic structures. And this is this generalized Riemann-Hilbert correspondence. And as before, this guy is a local system of moduli spaces. And I just want to return for a second to previous picture. So here, the fact that this local system of moduli spaces, sometimes people talk about this by talking about isomonodromic deformations of a differential equation. And so they just say that you can vary the parameters on your moduli space in such a way that topological parameters remain the same. So that's isomonodromic deformation. And this happens because you have this local system on the right-hand side. You can talk about this. And here you also can talk about isomonodromic deformations because it's a local system. And for me, the important upshot of all this discussion is that there is a certain group, let's call it gamma alpha D. This group is a fundamental group of the corresponding connected component of this moduli space. Now, once again, why this wild moduli space is much bigger? Because if you talk about a formal solution of this differential equation, so this means that you have a Puisy series like that, it has parameters, it has this kind of exponents which contribute to discrete data, but it also has this discrete parameters. And so, continuous parameters, lambdas, and these lambdas, and also coefficients here, they contribute to this wild moduli space. So this is some big moduli space which lives over MGN. All right. So what this lecture, I stop here the analytic motivation for the subject. And so what I wanted to do, I wanted to explain the following theorem. After that, even if you feel that you were lost in this kind of motivations, after that, the exposition will be extremely elementary and you can start listening from scratch. But I just wanted to motivate why we're doing this. Okay, so the theorem is the following, that first of all, there exists a non-commutative moduli space, that's called stack, which we can call M Betti non-commutative, which depends on this discrete data somehow. And it is equipped, of course, with an action of the wild mapping class group. Which was just introduced, gamma. That's the first part. And the second part is that it has some interesting structures, even as a non-commutative stack. For example, the stack of Stokes data. This is the non-commutative stack of Stokes data I was referring to in the title. It carries a non-commutative cluster Poisson structure. So I have to define what this means. Which is equivariant under the mapping class group, a bild mapping class group. So this statement, first of all, I want to explain a little bit what does this means. So, for example, this means the following, that if you have some non-commutative field R, so it's called a skew field. For example, you can take R as a complex number, so quaternions or something else. Then you get a set. So you get a set of points of this non-commutative space of Stokes data with values in this non-commutative field and the mapping class group X here. And actually, you can try to do the same for any ring. And then I have to be a little bit more careful talking about points, because I have to assume that some elements of this field, of this ring, are invertible. But this is morally what's going on. So morally, you can take R to be matrices of arbitrary size. And the story should be uniform in these matrices. This means that you are not allowed to use matrix coefficients of these matrices, but deal only with matrices. And so the claim is that this algebraic variety, which is the usual commutative algebraic variety, it has some kind of upgrade where you allow now to take its solutions of those equations with values in arbitrary rings. But as you will see, when it's a moral idea, so I'll explain exactly what happens a little later. So that's first thing. And the second thing is that you can actually take the classical situation, complex numbers, and then we get the fact that Moduli space of Stokes data carries Stokes data carries gamma invariant, equivariant cluster Poisson structure in the usual sense. So this on its own is a very interesting statement, because this implies that it can be quantized in a strong, in a cluster sense. In the sense we were doing this with Volodya Fock. So once again, upshot of this main result is that if you forget about non-commutative rings, that all Moduli spaces of Stokes data related to arbitrary differential equations can be quantized. Okay, so now let me actually start the careful exposition of what's going on. And so, as I said, I'm going to be very, very elementary, so you can start listening even if you think you were lost before. The story is, as I said, the most important part of the story is that the idea is that we have to deal with flags. And so I will start with a key example. So this is, any questions for now? No questions? Okay. So we want to describe configurations of flags. So we have R, which as I said is a skew field. Then we have m-dimensional vector space. And we have a notion of a flag. Flag, as usual, this is just a filtration. So we have a collection of flags of, actually, sorry, I use the upper indices. So this is a decreasing collection of flags. And I assume that the codimension of Fk is just K. And also, I want to consider a little later associate graded, which is defined as codimension I divided by codimension I plus 1 subspace of this flex. So these are flex. And now the first question is how to describe generic pairs of flex. It's trivial to describe flex because they're all the same. They're all equivalent by the action of the group. How about generic pairs of flex? So let's denote them AB. The first question is, what does it mean generic? So let's define this. There's only one definition you can imagine. So if you have your vector space, it projects to the quotient by A-dimensional subspace of first flag and also by the quotient of B-dimensional subspace of the second flag. So assume here that A plus B equals precisely 2 dimension of the space, and then the condition is that this is an isomorphism. So that's what means generic. Now we can, as I think everybody knows, we can classify generic pairs in the commutative case, and this works in the non-commutative case just as follows. So what we do, we now consider, we take now a pair of integers a plus b such that a plus b is m minus 1. And so this a and b are non-negative numbers. And we consider intersections of the corresponding subspaces. Now, because of the condition I put, it's one-dimensional. So we call it L b plus 1. It's a line. So it sits in our vector space. And if you consider direct sum of these lines, then it maps and actually isomorphically to our vector space V. It's an easy exercise. It's equivalent to the fact that the pair is generic. And so the simple lemma in this case says the following, that if you consider groupoid of generic pairs of flags, in our m-dimensional space, this groupoid is equivalent to another one. So this is groupoid of ordered decompositions into sum of lines, or I would just say ordered collections of lines, L1 and so on, Lm. And the equivalence works as follows. So the vector space is reconstructed as a direct sum of those lines. And then if you want to reconstruct the flags, then you either look from the left and get a filtration, or you look from the right and get the second filtration. So this is the pair of flags assigned to this collection of lines. And this describes you how you go this way. And how you go the other way, I already described. So you have generic collection of flags. Then you take the corresponding intersections, which are one-dimensional. Okay, so as I said, this is quite trivial and very well known. Now the question is, what are we going to do if we have triples of flags? Once again, why I'm doing this, remember that when we were talking about this model space of Stokes data, we realized that we have lots of flags and they are in some position each to the other. And so the question is how we deal with this problem of linear algebra, how we classify collection of flags in m-dimensional vector space over non-commutative field. And so the first example was trivial, but the second one is very non-trivial, and somehow it contains it is the whole matter. So how to do this? So we consider now triples of flags. ABC. in m-dimensional vector space. So we want to classify them somehow. First of all, we want to consider only generic triples of flex. And so we want to define what generic means. As before, we take triple of numbers a, b, and c, such a plus b plus c equals m. So these numbers are non-negative. And then, as before, we have v mapped to three quotients: v by a sub a, v by b sub b, and v by c sub c. You can do this for any triple ABC, and the condition is that this map to direct sum is actually an isomorphism for any such triple of numbers. It looks like a natural definition, but I want to warn you that this is not the only possible definition. For example, you can dualize this picture and you get a notion of generic triple of flex in the dual space. And it's quite interesting that this notion is different. So there are at least two different but reasonable notions of generic triples of flex, but I deal with this one. Okay, now really the main point is that in order to understand what's going on, you have to draw some geometric picture. So I take a triangle and you think about this triangle later as a picture for three flex, because this flex somehow sit at the vertices of this triangle called ABC. But then you put a bipartite graph corresponding to this triangle. It's defined as follows. So it has black and white vertices. That's why it's called bipartite. And I draw it the following way. So that's what you do when m equals to 2. Now, if m equals to 3, you draw the following picture. So now you put 3 black points on each edge of the triangle and do something similar to what we did before. So you put white points like that. And then you can still put the black points inside. And so you get a graph like that. So this is the case when m equals 3. And so I hope it's clear from this, what do you do for arbitrary m? Is that clear?
Yes.
Okay. So then the main result is the following. It's a theorem. There exists canonical equivalence between the following two groupoids. So the first one is the one you want to understand. So this is generic triples of flex in an m-dimensional R vector space. And the second, this is actually the main thing which happens, that it turns out that one need to consider flat R line bundles on the graph, which you call graph gamma m, which was introduced before. So this is the graph gamma 2, and this is the graph gamma 3. And I want to stress that the graph involves this, but it does not involve the triangle. So this is the graph I'm talking about. It's a bipartite graph. At the moment, this makes plays no role, but this yellow graph is the graph we're talking about. So what does it mean? So forget about groupoids, but if you just want to understand the isomorphism classes we're talking about here, that then what you learn that in the case when m equals 2, there is no parameters. So there is just one local system because the graph has trivial topology, this graph. But this graph already has non-trivial topology. And so here's what the theorem says when m equals 3. That the right-hand side of this correspondence is given by one-dimensional local systems on a circle. And we have to take its r points. And this is r star divided by the r star conjugation. So already the bottom line of this, that this is a description, but we cannot describe it by coordinates, because if the field would be commutative, then here we would have just one coordinate, the monodromy. And so we can say then that the parameter is given by just one non-zero complex number. But in the non-commutative case, there are no coordinates. So, and in general, if R is commutative field, for example, complex numbers, then we have canonical coordinates, and the number of them is m-1 choose 2. And these coordinates are monodromies around the holes. Okay. So, for example, here you clearly see that you have one hole, and that's where the number sits. But if R is non-commutative, I stress this again, then we have no coordinates. So those coordinates which you see in the commutative case, this canonical coordinates, that's exactly the one which we considered with Volodya-Fock long ago. But saying again, the main lesson is that in the non-commutative case, there are no coordinates. So you have to, therefore, we have to change the language in which we talk about this kind of things. Now I want to, so first of all,
may I ask, what are the basic examples of R which should be kept in mind? Correspondence or something different?
Well, the main example of R is matrices. They are not quite fields, but when I'm talking about, but it's really the main example. And so I want to define, so this means that I want to define generic triples of flex in a vector space which has dimension m times some big number n. So it's like m times n, and n is a parameter. And I want to describe this vector space, this collection of flex in such a way that this n really enters as a parameter, that all it will be, everything will be over matrices over n, but I'm not allowed to talk about the matrix coefficients. I have to deal with them as kind of symbols. And so if I want to get a clean formulation without explaining to you which linear combinations of matrices I want to be invertible, then I'm talking about skew fields. And there are plenty of skew fields, but what I have in mind is just matrices. Is that okay?
Maybe yes. So I understand that we should consider matrices which are actually not just numerical matrices, but something with coefficients being elements of some commutative algebra on?
I would say this complex coefficients. You can put any commutative algebra if you wanted, yeah. So
in the sense that we say that any matrix is invertible, in the sense that it's invertible everywhere except the loops where its determinant is zero.
Yes, so if you formulate this for matrices, then we will have not a clean one-to-one bijection between the objects, but we'll have bijections between the risky open parts of both sides. But I wanted to have such a description which is universal with respect to this ring R. Okay. I want to have kind of functorial and universal description which works for the arbitrary non-commutative ring field. Okay.
Yes.
All right.
Sorry,
Yeah.
gamma M is the internal vertices, right? Like the graph in which we take
the graph is a yellow one. So for example, this graph, this is a graph. So what I mean is that this triangle, which I draw here, is really irrelevant. So this is a graph, okay?
Okay, so why is it the circle S1?
Oh, but this is a graph. So, okay, maybe what is confusing is that these little circles are vertices. They're just a notation for vertex. It's just a vertex of different color. Maybe I can make it black. Oh, sorry, red. Now it's less confusing, yeah?
Okay, so there is no face inside. The green one is not the face. Okay, I understand. Thank you.
The green one, this one is the face of the graph, yes, because
Yes.
there is a loop here.
Okay.
Okay, but there's only one face of this graph. So this graph topologically equivalent to a circle. And this graph topologically is a point. And if you draw a graph for m equals 4, it will be actually three circles. Yes.
I'm sorry. When you say it's the face of the graph, you have to say that it is not included in the graph. It's not a part of the graph. Otherwise, it would be contractible.
Who is not the? I mean, green is not a part of the graph.
It's the whole rather than face.
It depends on your terminology. Sorry, it's if you're talking about Riemann graphs, we call.
Yeah. But the question was whether the face belongs to the complex. It doesn't belong. The two-dimensional cell is not included.
Yes, because I have one-dimensional graph.
Yeah, but that is how I understood the question.
Okay.
I'm sorry.
Thank you very much.
Okay. All right. So, so that's the claim. Now I want to prove the claim. So the proof actually is very elementary. And so I will give a complete proof. So first of all, okay. First of all, let me explain how you go from generic triples of flags to a flat line bundle. On the graph gamma m. Well, let me recall what is a flat line bundle on a graph. So a flat line bundle L on any graph, for example, gamma m, is the following data. First of all, you have to give yourself a line, one-dimensional vector space, which sits at every vertex. And secondly, whenever you have two vertices which are connected by an edge, let's call them V and W, you have to give yourself an isomorphism from LV to LW, and this is supposed to be an isomorphism. That's all we need to do to construct local system or bundle with flat connection on the graph. So this means that it's a good idea to understand how to think about the vertices of our graph. And in our case, this kind of vertices, you can call them white vertices, or they actually were red on the picture which we eventually made. So this, I still call them white vertices. They're in one-to-one correspondence with the triples of numbers A, B, C, such that A plus B plus C equals M minus 1. So, for example, so here you have 3 vertices, and they correspond to triples like 0, 1, 0, 0, 0, 1, and 1, 0, 0, and so on. So they are just solutions of this equation. Now, since A plus B plus C is M minus 1, it asks for introduction of a line, and so the line is the intersection of the corresponding subspaces of the flag. And we want to denote this line L by putting this white vertex there and putting indices of this white vertex. So this is the lines which are going to sit over white vertices. Now, for black vertices, it's a little more complicated. So first of all, how we parameterize black vertices. So these black vertices of gamma M, they're in one-to-one correspondence with the similar solutions of the equation, but now where A plus B plus C equals M minus 2. You can check, for example, that in this case, actually, I'm talking about, I want to talk about only black vertices which sit inside, but at the moment it's not very important. And so in the M equal to case, there will be only one solution, 0, 0, 0. Let me kind of write it here. This vertex is parameterized by 0, 0, 0, and this vertices I don't want to consider at all. Okay, now because the codimension, the sum is M minus 2, it asks for a two-dimensional plane, which is defined by the same way. And so this is a plane, ABC. Okay. Now what happens if you have this black vertex? So it is neighbor of 3 white vertices. And if you consider the labels, so the label of this black vertex is what's called A, B, C. And the labels of the white vertices are something like A, B plus 1, C, A, B, C plus 1, and A plus 1, B and C. Okay. So this means that we can make the following diagram of lines and one plane. So we can consider in the center the plane which we just introduced, plane ABC, which corresponds to the black vertex. And then there are 3 lines which are mapped to this plane. It's very clear what the lines are. They correspond to the 3 white vertices. And if you want, I can label them A, B plus 1, C, or A, B, C plus 1, or A plus 1, B, C. And so we get the following diagram. So plane and 3 lines. Okay, how actually we get this diagram? In order to get one of the embeddings, for example, this one, we have to notice that A plus 1 sits inside of A sub A, and that's how this embedding is induced. But we still want to have a line over black vertex, not a plane, and so we introduce the line by the following way. So the line attached to this black vertex is the kernel of the natural map from these three lines assigned to the white vertices to the plane. So again, you can put indices here, just put one of them. Okay, that's clear? So we have three-dimensional space given by the sum of three lines here, and it goes to two-dimensional space. The kernel is one-dimensional. And so now we get what I promised, because I have my graph and I have at every white or black vertex with this graph one-dimensional vector space. But they also come with natural maps to each other, because if I take this middle one line which sits over black vertex, it naturally maps to the lines which sit over the line vertices. Just by construction, because this line here, it sits as a subspace here, and therefore it projects on each of these factors. Summands. That's it. So the construction is finished. So we got a local system because we have lines at vertices and maps between them, which are isomorphisms. Are there any questions about this? Okay. Then, if there are no questions, I want to explain how we go back. What is the inverse functor? So this is a reconstruction functor. And what we do, we consider now flat line bundles on the graph gamma m, and we want to construct triple of flex.
Excuse me.
Yes.
But do you actually consider the quotient of flat bundles by some group acting at vertices or not?
No.
No, just set of all flat bundles as you described, not equivalence classes, right?
No. I said in the beginning that we consider groupoids. This means that we consider this line bundles and isomorphism between them. So this is answer to your question. This is equivalence. I mean, scientifically, this equivalence of categories. The objects are those line bundles and the isomorphism between them, and so this answers the question. This is actually the reason we are talking about groupoids.
I see. All right, thank you.
So it is just we construct two functors. One of them take triples of flex and produce line bundle, and the other, which I want to define right now, takes a line bundle and produce triple of flex. Okay, so how you do the second construction? So you have a flat line bundle L. So what you can do, you can take the fibers of this flat line bundle on black points and at white points, and you take direct sum of them. And then there is a parallel transport. So you get a map from one to the other. And so let's call this operator K. In this black and white business, this is a version of this Castellan operator. So now what we do, we introduce a vector space V sub L, which is just co-kernel of this map, K. And this is a vector space where our flex are going to sit. And now who the flex are, it's quite clear if you go to the picture. So if you take this picture, then let me explain. Just want to delete what is unnecessary here. So here you have one vertex, for example, vertex A. And so what we want to do, we want to filter this picture the following way. And now it's very easy to see that this filtration is a filtration on the complex, and therefore it gives filtration on the co-kernel. And that's exactly the first flag. And you do the same with the other two vertices. And I wanted to stress that this picture is very important. So I want, in the more intrinsic to graph terms, I can think about this filtration as a kind of the one which corresponds to this kind of passes on the graph. So this is so-called zigzag passes, and they will play a fundamental role in the whole story. So what I'm saying here is that I consider the zigzag passes which are somehow related to the vertex A. And then there are two other kinds of zigzag passes, and for the vertex B and the vertex C, and this way we get triple of flags. And then it's very easy to see that by definition, these constructions are inverse to each other. So that's it. So that's the proof of the theorem. And finally, if your ring or field is commutative, then as we discussed, you can just calculate the monodromies of this local system over the faces. And then you will recover the invariants, which are precisely the one which we introduced in this Volodya-Fock when we were playing with triples of flags. But once again, the important difference is that in the non-commutative case, this is a language to think about this, and there are no coordinates. You cannot avoid talk about local systems if you live on the non-commutative world. Okay.
And at some point, you disregarded the outer black vertices. Do you consider them now?
Sorry, what?
At some point, you disregarded the outer black vertices. Yeah, because the solutions of the sum equals m-2 or m-1 were only the inner black vertices.
I guess I consider them now.
You do, okay.
But as far as I remember, I consider them now, yes. So for example, you can look at this example. Where is this? Okay. Actually, no. So just sorry. So I don't consider them because I want to get two-dimensional space, and otherwise I don't get it. So I have 3 minus 1. And in this case, you can count, you get 6 minus 3. That's 3. So thank you for the question. So I really disregard that. Okay.
Thanks.
More questions?
So what you did say just a minute ago, do you understand that morally the I don't know how to say category of local systems on a graph play the role of coordinates for which would actually be the coordinates in the case of commutative field, but now they replace this tool, right? Oh.
Exactly. This is the main idea and the main message. Absolutely.
Okay.
The main point. The main point is that we have to change the way we think about cluster coordinates in the Poisson situation. There is no function, no coordinates, no Poisson brackets to consider because there's no functions basically. If you think about this way. So we have to rethink all kind of notions, but all of them exist if you think about them in the right way. And the beginning to think about them in the right way. And the main point is that, first of all, you have to consider graphs. These graphs turns out to be bipartite. This turns out to be extremely important that they're bipartite, as you will see. And we have to consider one-dimensional local systems on those graphs. Okay?
Very good. Thank you.
Thank you for the question. So you really helped me. So this is really the main point. Okay, actually I said graphs, as you'll see a little later, you may deal with surfaces as well, but I have to explain how. Okay, I want to do one more kind of comment on this. So I want to define this reconstruction factor in a different way. So So reconstruction functor revisited. And again, going back to commutative, non-commutative situations, so as I already said, I just want to repeat just to make things clear, that when you're in the commutative case, when you look at this construction, you discover that actually we were doing what we are always doing. So because we literally reconstruct what, by taking monodromy as a construction which we are playing with Volodya-Fock, but we didn't speak this language. So this language of bipartite graphs, it's the adequacy to this whole story was realized a little later, and there's actually my paper somewhere like 15 something was called ideal webs, which explains this point in the commutative case. So that's it. So you need bipartite graphs and local systems to talk about cluster Poisson coordinates. All right. So let me do reconstruction functor in a different way. So once again, let me consider this picture. Okay. So I wanted to consider some kind of passes on this graph. Just a second. And so what kind of passes I want to consider? I want to consider passes which go like that. So I can go like that. Or maybe I can go like that. So I start with a certain vertex here. So for example, I can start with a vertex V3. And then I want to go to some other vertex. For example, I want to go to vertex V2, different vertex here. And then I want to draw these pictures again, although you already see how it works for one vertex, but for this particular vertex, so I can do it this way. I can go this way, or I can go the other way. Let me do it in different color. You can go like that. Okay, so I hope it's clear what I mean. So you go from one vertex to the other in the shortest possible way. And the second vertex, this is all somehow adjusted to one of the vertices, let's say vertex A. This is whole story. And so this kind of snakes passes. So they go in the shortest way from one vertex to the other, and the other vertex has distance less from A than, or equal than the first vertex. Okay, so let's call such passes A passes on gamma n. And then if you look at this picture, then there are actually j-1 to I-1 A passes from vertex Pj to vertex Vi. And I'm going to use this passes in order to construct a vector space in 3 flags in the following way. So first of all, I pick a side AB. Then I consider this side. So this is my side AB. And I assign to the side a vector space. So this vector space VAB is just direct sum of my line bundle sitting on the vertices of gamma, gamma M, which intersect the side AB. So in the case I was talking about these vertices. So in this case, the space is 3-dimensional, as you see it. And now I want to describe isomorphism between one space and the other. Phi A B goes to C. This is going to be isomorphism from this green one to the blue one. So it's a map from VAB, one vector space, to VAC. And it's given just by a very simple formula. This is just A, B goes to C, is by definition, is just the sum over all parallel transports over this passes corrected with a certain sign. That's it. And so I claim that first of all, this is an isomorphism. And secondly, that if you have your triangle, then you have now 6 isomorphisms, this one, and this one, and you can go backwards. And I claim that the composition of the 3 of them is identity, and the pairs of them are mutually inverse to each other. So the claim is that if you consider composition phi B C to A composed with phi C A to B composed with phi A B to C, this is identity, and they are mutually inverse to each other. And therefore, the conclusion that we can identify the 3 vector spaces which we called VAB, VBC, and VCA, and we get a configuration of 3 flags in each of them identified. So that's exactly the data which you want to have. So this construction of looks different, but actually, if you look at the definition, so you can see that it's just equivalent to the one we were talking about before, but phrased in a quite different way. So that's the end of the story about triples of flags. And now let me ask you, are there any questions about the story? Or I can proceed further.
What would happen if we would consider a quartet of flags? Would we have a tetrahedron or a square?
Square. But wait a second, I'm going to talk about this in a second.
Okay.
I want to finish with triples of flags.
All right.
Okay. Are there any questions? Okay. So if there are no questions, let me proceed actually to the general situation. It turns out that this description does much more than it looks like. So I want to go to the next topic, which can be called spectral description of non-commutative character varieties. And let me make the corresponding definition. So I start with a surface, which is a surface with punctures at the moment. So I called S. And we consider the modular space of local systems here, which is just representations to GLMR, where R is our non-commutative ring, considered modular conjugation. And this is, of course, the same thing as m-dimensional R vector bundles with flat connection on S, model isomorphisms. And well, the point is that there is no good description. It does not exist. So, for example, even in the commutative case, this modular space is can be non-rational. In general, it's not rational. There are no coordinates, no preferred coordinates. So it's not a great object to consider. So, I mean, it's a great object to consider, but you don't get a good answer. No good description. I mean, you can disagree, but there are no coordinates at least. Oh, sorry. the reason there are no coordinates in general because it's non-rational. But there is a fix to this. So it's a little surprising that such a fix is this, but there is a fix. So we can consider slightly different moduli space, which we call XMS. And this is almost the same thing. It's m-dimensional vector bundles on S plus invariant flex near the punches. Invariant flex means that you have a local system and you put some flag here, and this flag has to be invariant under the local monodromy, but of course not about the global monodromy. And there is, in general, there exist m factorial such flags near each puncher. And so this just means that this moduli space is a cover of degree m factorial raised to number of punchers of the moduli space we wanted to consider, which you can call it m-dimensional local system on S. And this cover is a Galois cover, so there is an action of the group S m to this number of punches acting here. And this space does have a good description. And so this is a space to consider, this one. Now, and it turns out that we basically already described this space, because what we can do, okay, in order to formulate the theorem, I have to draw one more picture. So it's answering the previous question. So let's make a triangle. And let's make another triangle nearby. This triangle is not part of the picture, it's just for drawing. And now let's draw the bipartite graphs we were talking about for each of the triangles. Okay, so let me do it in red. So okay, and you do exactly the same thing for the second triangle.
I feel you draw it every day. You're
well
trained.
No, you haven't seen the real professionals in this business. So it's like my Rick Canyon. So when he draws a graph, that's really a piece of art, but this is a little ugly. But anyway, so now let's remove these triangles so they don't confuse you. So we keep them in a kind of way like that. So you get a graph. Now you can keep going. So if you have more complicated triangulation over surface, then you can put these graphs inside. And so all in all, altogether, you see that if you have ideal triangulation of S, then you get some bipartite graph which can be called gamma m of S. And now there is a theorem. I can label this theorem X related to S, that there is this canonical Zariski open embedding, where on one hand side you have, oh no, you have flat R line bundles on this graph gamma ms. That's an open embedding. On the other hand, you of course have this moduli space, which we consider xms. So for each ideal triangulation, you have such an open embedding, but actually you have more embeddings because maybe not now. I will try to explain that there is some condition on a bipartite graph which is inscribed into the surface, which allows to do this. And so these were just some examples. And so this means that in this moduli space, which we considered, we have lots of non-commutative tori sitting inside, because this flat R-line bundles on any graph is like non-commutative torus. If the field is commutative, it would be a split torus. And so this is a non-commutative analog of cluster of a given cluster coordinate system. Of a cluster Poisson coordinate system.
I beg your pardon, but the vertices of the triangulation, not the graph of triangulation, are
not part of the story. Not part of the story.
But are they punctures of the surface?
They are punctures. Yes. This is
so they are
ideal.
They participate in some way.
What?
But don't you have to require that monodromies around faces of the graph, small faces, I mean, are trivial or not?
No. This monodromies are the coordinates. Why they should be trivial?
I thought that in this case, the coordinates are monodromies in our around big loops, not small ones.
Sorry, there is no small loops on the picture. If you see some,
but in your picture there are, say, 6 gons, or
6 gons are not. 6 gons are the holes which you're talking about. There is no other loops. If you see loops, this is just black points.
So I'm somewhat confused. I thought the surface has pi1, right?
Yes.
So the resulting graph has big loops in this sense, reflecting this pi1, but there are small loops which are contractible on the surface.
Yes, but nevertheless, we do not consider them with the surface. We consider them just as a graph. So the monodromies around small loops are the key players. They are the coordinates in the commutative case. In the non-commutative case.
The graph is not homotopically equivalent to the surface. Then why?
The graph is absolutely not homotopically.
Yes, right. Now I understand. But then I don't understand the embedding.
I just explained the embedding. So you take, let me give an example. So you take a punctured torus. Let's say you take 2 punctured torus. This means that you glue torus this way. And so these points you glue together. This is one puncture. And then you put another punch inside. Then you consider triangulation of the surface, called ideal triangulation, as you know, because all vertices of triangulation are as the punctures. And so we have 4 triangles in this case. Now you insert in each of these triangles a graph. You insert the standard graph in each of the triangle. And then you get some, if M is big, you get some very, very complicated graph with lots of holes. So this is a graph which corresponds to this particular triangulation of twice punctured.
Yes, this construction I do understand, but how the flat connection on the graph can be, no?
Alyosh, it's different stories. You have connection n-dimensional bundles with connection on a surface, or you have a graph and linear bundles there.
Yes. Sorry, I was confused. Now I understand. Thank you.
Thank you, Boris. So you are just right. So the whole point is that you can express, as just Boris said, m-dimensional flat connections on.
Yes, I've got it.
As one-dimensional flat connections on a different topological object, which at the moment is presented to us as a graph, but can also be presented to us as a different surface, the spectral surface.
Yes, very Interesting. Okay, okay. Thank you.
I have 90 minutes, so I have to. Oh wait, no, I started 40, so I still have 10 minutes. Okay, so now let me prove this theorem. The proof from what we've done is just one line, basically. Yeah, so this is a theorem. Let me prove it. The proof is this. So we already know that if you take this triangulation, you can put some m-dimensional vector bundle to each, m-dimensional vector space to each of the faces, to each of the edges of this triangulation. This is the construction which I call the reconstruction Fanta revisited, this one. So you have now, once again, you have this, remember you have the sides, on each side you have m-dimensional vector space, and then there are maps between them which corresponds to oriented angles of this triangle. And so now you do the same here, and you have lots of vector spaces sitting on the sides, but they're all related by isomorphisms, and altogether this is just a local system on the surface because triangles topological trivial, that's it. So the proof after triangles, the proof is one line. Okay? Is that clear?
Yes, now I perfectly understand. Wonderful. Thank you.
There is, however, an issue with this, because this is good, but this is not that good. So the actual theorem is that it's some kind of addition to this, that so it's like a version of this theorem, that the mapping class group action on XMS preserves the structure. I mean, the point is that this construction is actually equivariant with respect to the action of the mapping class group, and it looks very strange because the whole construction was based on triangulation of a surface. If you apply element of the mapping class group, you get very, very different triangulation of the surface. And what is worse, these graphs inscribed in the triangle, they will change in a very dramatic way. But even if you consider quadrangle, as Lyosha was suggesting in the beginning, so you can consider this triangulation or that triangulation. So they're related by classical flip. But if you consider the graphs which are embedded here and here, they're very, very different. And it turns out that there is some kind of fact that any two such bipartite graphs can be related by a sequence of elementary transformations or elementary moves called 2-by-2 moves. And I'll explain this in a second. So this theorem, this fact is proved in my paper, Ideal Webs. Why I refer to this, because you can just see the pictures. It's proved by drawing pictures. And I'm not going to draw them. It takes lots of time in real time. But they are related this way. And I can explain at least what happens when m equals 2. When m equals 2, if you think about triangulation, I can assign to this bipartite graph, different than the one I consider, but still I can assign to this kind of bipartite graph. And then if I consider a rectangle, I get a more complicated bipartite graph. Now, if I consider flip, then I have a different bipartite graph. So you have again 4 vertices sitting here, but now the black vertices are located in a different way. And so now I get a move, which is called the 2 by 2 move. That's a definition. So now I erase those sides which are not part of the picture, and so this as well. And so I get some transformation, which is now, I think, well motivated. So just corresponds to elementary flip. So this transformation is what's called 2 by 2 move. And the rest of the graph, so you consider this sitting inside of a certain graph. And so the rest of the graph is fixed. It's just a local transformation of the graph. And I claim that there is a way to alter, there is a way to transform local systems on one graph, let's call gamma. So we have graph gamma here. And we have a new graph gamma prime. And this is some kind of map. The claim that there exists canonical birational isomorphism between one-dimensional local systems on one graph, non-commutative local systems, and one-dimensional local systems on the other graph. This is birational isomorphism, and it's defined just by drawing a picture. So, okay, to draw this picture, I want to draw this procedure once again, a little bit more carefully. Okay. Let me do it just since I'm drawing picture, I drew it, I changed the colors. So now I drew this picture. So you can interchange the colors. And so this relates to a picture which you draw this way. Okay, and now I have to tell you what happens with local systems. But for example, I need to tell you how you parallel transform. What is this parallel transform is? So here the parallel transforms on the left are given to me, but on the right I have to define them. And so on the left, what I do on the left, I consider the following two passes. I consider this pass, and I consider also the pass which goes around. So I call this pass T, or this parallel transport T, and this is T tilde. And this one is the one which I wanted to define. This will be T prime. And so the formula is, it's a definition that this T prime is defined as T plus T inverse, or what is the same, this is 1 plus monodromy at the point, starting at the point B, in which goes counterclockwise, applied to parallel transport of this graph T. So that's it. So this is a transformation. And this way I can identify moduli spaces of line bundles on one bipartite graph and another bipartite graph if they are related by this elementary transformation. In order to prove now that I can relate any two bipartite graphs by these moves, in particular the ones related by triangulation, I first of all have to prove that any two bipartite graphs are related by a sequence of such elementary transformations, and I'm going to skip this. But I also need to give you complete formulas, because what I did, I showed you example, but if you think that the same things will happen with transformation like that, it's not quite true, so this will be different. And so let me first of all give you an actual correct definition, and then state the theorem about this. So if you want, so okay, so I have to label the vertices here. So this is A, B, C, D, and this is A prime, B prime, C prime, D prime. And Now, the definition works as follows. If I want to consider the parallel transport from A prime through the black vertex to B prime, that's a notation, then I define this as 1 plus monodromy of B applied to the parallel transport from B to A. That's what I said. But if I wanted to do it from C to B, from B prime to C prime, then this is T C to B multiplied by similar expression, but from the other side and inverted. And then there is a cyclic shift by 2, so I can do the same for D prime C prime. This is 1 plus MD translation D to C. And there's similar translation A prime, D prime to A prime is defined as translation from A to D and then multiplied by 1 plus MD inverse. And the main theorem about this, that this 2 by 2 moves satisfy the pentagon equation, pentagon relation. What is pentagon relation? It's crystal clear because remember that the 2 by 2 move is a flip, basically. And then we have 5 pentagons related to changing triangulations like that. I believe everybody understands what I'm doing here now. And then, of course, the statement is that the composition of these 5 transformations is identity map. And you actually don't even check this directly. You check this by using the theorem which I already formulated, but because all these 5 description of the same object, you basically consider just a configuration of 5 flags. We have 5 flags in a 2-dimensional vector space, and there are 5 ways to describe them, this, and this. But since they describe the same object, the pentagon relation must hold. Okay, so that's probably it for today. So what I did, I described non-commutative structure on, I described the analog of cluster Poisson description for non-commutative local system on a surface. So next time I'm going to actually explain what is non-commutative cluster Poisson structure, explain what is a Poisson structure, and then explain the created version of this, and then explain what happens with the Stokes data. So I guess that's it for today.
But just to make sure, if you go if you go back from right to left via the same 2 by 2 move, do you get the initial data?
Certainly. Otherwise, I wouldn't be talking about this.
Okay.
Yeah. I mean, the point is that these formulas, they appear not out of the blue. So what you do, you take this picture and you take this picture, and these 2 pictures describe the same object. They describe your configurations of 4 lines in 2-dimensional non-commutative space, but they describe it in a different way, but the same object. So if you find the way how these 2 descriptions are related, it's by definition is going to be self-dual. And it will, by definition, satisfy pentagon relation. So this is how these formulas were obtained, but actually it's nice that they're very simple. And if you ever have seen this cluster Poisson business, they remind you what happens there, but then kind of different flavor, but still you can partially recognize that they're similar to the formulas which we write in usual situation.
Sasha, but could you please motivate geometrically these particular formulas for?
I just did. I
did not understand, because I clarify my question. If I would consider commutative connections and would be interested in moduli space of flat connections on the graph. I would, these two graphs related by this elementary flip are homotopically equivalent. So actually there is a other natural way to identify moduli spaces on those two graphs, and the formulas would be different.
No, but you don't do that. So you don't treat them just as graphs.
Yes, I understand, but how do you choose geometrically this way of writing formulas?
As I said, so look, so we already know
it's not geometrical. I mean, okay, maybe I'm not clear.
You take triangulation, and then you take two triangulations. You triangulate. Wait. Then you have 4 flags. Let's call them A, B, C, and D. Yes. Then you already know what to do with triple of flags. So you already know what to do here. You already know what to do here.
Yes.
And so you record what you know by writing these 2 bipartite graphs. Because what happens in one of them, for example, on this one, so you have a description of this using bipartite graphs. So you draw these bipartite graphs. And you also notice that this picture will be somewhat different than the one I was talking about here. But nevertheless, they're closely related. So, I mean, draw the bipartite graph. So it's... and just you have in your hands this isomorphism, this identification between flags and pictures on these graphs. And you have a similar identification on the right-hand side for BCD triangle.
Yeah.
But you can go back and forth between configurations for flags and these line bundles in a very, very explicit way. Then you do it in a different way. So you draw a different triangulation of the same story. You have the same flags. It's 2-dimensional, A, B, C, D. And then you again have 2 ways to... You have these 2 triangles, and so you again inscribe bipartite graphs as I just did before. So something like that. And you get your description, but there will be now different descriptions. And as you will see, you will have here just one whole, and which is important for us, but still you describe the whole local system. Then just if you write down formulas, then in a few minutes you will get the formulas which I'm talking to you.
Okay, thank you.
But again, it's kind of nice that you can recast all commutative story, which some of us get so much used to in non-commutative terms, but going to line bundles and talking about monodromies rather than coordinates and so on and so forth. But the message is that everything can be translated in different language, and now it actually gets, from my sense, much more clear.
So I wanted to ask, what is the difference between non-commutative local systems with group GLM of R in the case when we put R equals some n times n matrices, and commutative local systems for GL n times n?
I understand what you're asking. So you want, let's say you have local system of dimension m times n. On one hand side, you can describe this as, you can look at this as mn dimensional local system. But on the other hand, you can give yourself a task of describing in such a way that you think about your matrices involved, m by n matrices, just as a block matrices, something like that. And so the question is, can you make a description in such a way that you really deal only with those blocks and never ever talk about the matrix coefficients here? So that's what happens here. So you describe the same object, but I will explain next time that, for example, if you're talking about Moduli space of two-dimensional non-commutative local systems. You can substitute matrix of size 100 by 100, and now you're talking about local system of 200-dimensional vector spaces. It is Poisson space, and so you can talk about its Poisson geometry, but on the other hand, you should talk about non-commutative Poisson geometry in such a way that if you substitute for your non-commutative elements this matrices and express, I will explain next time what is a Poisson structure. If you calculate this Poisson structure, you're supposed to reconstruct the one which you had on this 200-dimensional space, but it will be a very different description. That's all I can say. And so you'll get map of one Poisson space to the other. So you can ask a philosophical question. So what's the point of doing all this? Maybe I'll give you some examples next time. So for example, there was this beautiful work of Gelfand and Retach when they talk about quasi-determinants. Again, they do exactly the same thing. They want to find something which is a determinant of 200-dimensional matrix in terms of its 400-dimensional blocks, and so they succeed. And what we're doing here is a kind of geometric language which actually explains a lot, if not all, formulas which appears in a kind. So we get them in a kind of forced way. So we do some constructions. When we try to calculate them, we recover quasi-determinants and relations they satisfy. So it's kind of coordinate-free way to do this. I would say geometrically motivated way to do this, which actually was one of the motivations for this story. I should say that this story, it's an old story. Old means that we were started doing this about 10 years ago, and Maxim gave lectures like in Gelfand conference here. But I'm glad I can do this now using more time, because one can never say this in 1 hour. And so, but I will connect to things like explicit formulas next time.
Yes. So, have I understood correctly that the answer is that these two constructions are a little bit different in the sense that one Poisson manifold will be a little bit bigger than another one. So, in the sense that on one side we have, for example, only some traces of monodromies, and on the other side we can have so kind of the traces of monodromies will be elements of some matrix algebra themselves, or
no, I absolutely agree with what you're saying, that they are not isomorphic. I said that there will be some maps of Poisson algebras, but they are not isomorphic. It shouldn't be isomorphic. So once again, we take Moduli space of 2 times or 3 times n dimensional local systems, and we try to get information, the part of the information about them in terms which is kind of universal in n. And so, I don't know. Like when people talking about matrix models, they have the same goal in a sense. I'm not sure if I answered your question, but try to.
No, I think you answered it. Thank you.
Mm-hmm.
Okay.
Hi, Sasha, can I ask a question? So,
Yes.
So you mentioned this A passes in some slides. So I was wondering if you take the sum of all those A passes from say I to J, so where it satisfies some Laurent phenomenon.
This is yeah. So if you take the signed, hello Linghui first of all, and if you take this second construction explains the Laurent phenomena. This is sort of the reason I was mentioning this, because the Laurent phenomenon now means that whatever function you're constructing is going to be given as an alternating sum with signs over passes. And this signs, as you understand, so in order to get rid of signs, you have to talk about twisted versions. But the point is that, yes, that Laurent phenomena means basically that whatever you want to calculate is sum over passes. But what you do with these passes, you parallel transform. And so in the usual situation, when we prove this Laurent phenomena, for example, for monodromy of local systems, if you look the way done, the way we're doing this with Volodya-Fock, it's actually I would say it's basically the same, because we were talking about some snake construction, which is very close to the sum of the passes, and then just got Laurent polynomials for taking different passes in our triangulation. So if you just decipher the commutative construction, you'll see that this is basically the same thing. But it recasted in a way which makes non-commutative, which is manifestly non-commutative.
I see. It looks very similar to something like the quantum trace map when you consider the passes on the boundary.
Definitely. I mean, it is a trace map, because if you just consider a loop on the surface and have these vector spaces, and so we have some kind of passes go around here. So this is trace map, yeah. Actually, we discussed this with you some time ago.
Yeah. Thanks.
Okay. But this is okay anyway, so don't want to continue this line. More questions?
Okay. So, and thank you very much, Sasha.
Thank you.
Thank you.
No, at least I like this lecture very much, and let us go further. Okay.
Спасибо. Okay.
Okay.
So once again, I just want to kind of little apologize that I start talking about this differential equation since the beginning, and it looks like completely unrelated to the story so far. But I wanted to somehow to motivate your interest to this combinatorics, that it's actually does something which is related to, I would say, general algebraic geometric question which you asked about the differential equations. But the way it works is very simple but combinatorial. So just be patient. If you want to see the Stokes data, you just be patient to absorb some combinatorics first. Okay.
Okay.
All right.
Okay. Bye.
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 Tomorrow on 2:30 p.m.
2:30 tomorrow. Yes. Okay.
2:30 there will be a first lecture of Shapiro.
Okay.
Thank you.
Okay.